This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
All right, welcome to the online recordings again. On one administrative note, I'm going to attempt to record the Wednesday lecture using Zoom from home, so I don't have to come into the work and potentially get exposed to the coronavirus. So I'm going to attempt to do that for the Wednesday lecture. If it works, then what happens is I'll upload the video to Canvas in the media gallery on Canvas. So if you look on the left-hand side of Canvas, underneath modules and so on and so forth, you'll find media gallery, and I'll try to post it there. So if it works, I'll send out an announcement to tell you that's where the video will be, and if it works, I'll do that for the rest of the semester or until this is all over with and we have to come back. All right. So if it doesn't work, I'll be back here in the room and recording it with lecture capture, but hopefully I can do it in Zoom and work from home. All right, so just to recap, we're talking about the income and substitution effect, and I want to recap what the income substitution effect is, why it's important, and how we actually find it. So remember, the idea here is that when our price changes, so in this example we have the price of X goes up, right? Therefore the budget line rotates inwards from about the vertical intercept. Right? So when that happens, there's two things that happen simultaneously. One is, when the price of X goes up, the relative price of X has gone up. That is, the price of X relative to the price of Y. That is, X has become relatively more expensive compared to Y. Right? We call the change in demand due to the change in the relative price, we call that the substitution effect. That is, intuitively, we say, if X becomes relatively more expensive, then we're going to substitute out of the relatively expensive good, X, and into the relatively cheaper good, Y. Right? So notice here, it's always the case that the substitution effect is negative. That is, if the price goes up, then you want to consume less of the good. You want to substitute out of the good and consume more of the other good. Right? Or the demand doesn't change. So I should actually say non-positive rather than negative, but it's easy to say negative. So substitution effect always goes in the opposite direction of the price change. That's one thing that happens. But the other thing that happens when the price of X goes up is that there's an income effect. That is a real income effect, not your nominal income, M. That stays the same when you change the price. We're only changing one thing at a time. But your real income changes. And we can see that, for example, in terms of X. Remember, real income is how many X you can buy with your income, and that's given by the horizontal intercept. But notice when the price of X goes up, the horizontal intercept is lower. That tells you the real income in terms of X has gone down. We can also see this, by the way, with the budget line. Consider any point on your original blue budget line there, other than the vertical intercept. In other words, any bundle where you consume a positive amount of X. Notice that all of those bundles are above the new budget line in pink there. That means none of those bundles are affordable now. So that's the sense that your real income's gone down. Whatever you could afford before, you can't afford now unless you bought no X before. In that case, you can buy exactly the same thing now, right? If you bought no X before and spent all your money on Y, you can do the same thing now as before. Because remember, if the price of X goes up and you don't buy any X, who cares, right? There's no effect on you in the real terms. But as long as you consume positive amounts of X, then those bundles that you bought before are no longer affordable. So that's the sense of what your real income has gone down. Now notice those things happen simultaneously, right? The substitution effect, the change in quantity demanded because of the relative price change, happens at the same time as the income effect, that is the change in quantity demanded because of the change in your real income. And we want to separate those two effects out. Why do we want to do that? So I gave you an illustration last week. So the idea here is, changing prices is a very powerful mechanism to change people's behavior. One thing about economists you learn is how powerful prices really are. So, for example, we said, suppose we wanted to reduce the levels of pollution. We know that petrol causes pollution, so we wanted to reduce the level of consumption of petrol. So we would say, well, okay, let's raise the price of petrol. Now, petrol is not a given good, so we know if we raise the price of petrol, we're going to lower the quantity demanded, right, downward sloping demand curve, right? However, usually low-income people spend a larger proportion of their budget or their income on petrol, right? They have to drive. Petrol is a bigger share of their income than it is for rich people, right? So they still have to drive, so they don't have to spend extra money on petrol. It makes them poorer in real terms, and we don't want that to happen. We want to say we want to change people's behavior to drive less, but we don't want to make them low-income people poorer. So what we're going to do is going to give them a rebate to eliminate the income effect. That is, make them just as well off as they were originally. All right, so now you can see why we need to separate out the change in quantity demanded from the price change into the substitution effect and the income effect. Right, we need to find out the income effect so we know how big of a rebate to give these low-income people so they're as well off as they were before, right, to eliminate the income effect. And we need to know the substitution effect to see how much will be the change in petrol and therefore how much will be the change in pollution from this price change, right, from this policy change. So that's the idea, and I'll give you a few other examples about increasing pension checks as a response to uneven inflation, where the relative prices of goods are changing, but there's also an income effect as inflation goes up. Your existing pension check, the real purchasing power has gone down. It doesn't buy as many goods as before, so we want to compensate for the income effect, but we still want the relative prices to change. Okay. All right, so how do we do that? So just to summarize here, when the price of a good changes, the quantity demanded changes from the original quantity demanded to the new quantity demanded, and that change in X, we divide up into two parts, the income effect and the substitution effect. We call the income effect the change in X due to the income effect delta XM, and we call the change in quantity demanded due to the substitution effect delta XS. And we want to separate out those two effects. Okay? So the idea here, as we said, right, we have the original blue budget line here, right, and then the price of X increased, and now we have the pink budget line. Right? So the two simultaneous things, two things happen simultaneously. The relative price increased, as we can see by the steeper slope of the pink budget line compared to the original blue one. And secondly, real income went down. We can see that the pink budget line has a lower intercept than the blue budget line in terms of X. Or you can say it in terms of the bundles on the blue budget line are no longer affordable on the pink budget line other than the vertical intercept. Right? So we say, okay, we want to separate out the income and substitution effect. Right? So what we want to do is eliminate sorry, I shouldn't say it that way. We want to separate out the substitution income effect. So what we're going to do is we're going to increase the amount of income to the consumer hypothetically, such that their nominal income is now M prime. But they still face the new prices. So that would give you this hypothetical red budget line here, right? So they face the new prices, that is the new price of X, with the price of Y we even changed, and you have a hypothetical income, nominal income of M prime. That gives you that hypothetical red budget line there. And then we can see that if that hypothetical red budget line keeps the real income constant, then notice that the choice that you made on the original budget line, the blue one, and the choice that you made on the hypothetical red budget line, right, the difference in the quantity demanded will be your substitution effect. Why? Because you're changing the relative price, but you can tell by changing the slope there. So you're changing the relative price, but you're holding real income constant. Right? By assumption, I said we've increased nominal income to M prime to keep real income constant. All right, so that change in the quantity demanded of X, going from the blue budget line to the hypothetical red budget line, will be the substitution effect. And you can see going from the red budget line, the hypothetical one, to the new budget line, the pink one, that's a parallel shift, right? We're keeping the prices at the new prices, so the slope doesn't change of the budget line, but we're just changing the income from M prime to M. So that's a pure income effect, right? So that's how hypothetically, we're separating out something that happens simultaneously. The substitution effect and the income effect happen simultaneously. But in our mind, we imagine we take the original blue budget line, we rotate it such that it has the same slope as the new budget line, but enough income to keep your real income the same, right? And then we shift the red budget line back down to the new budget line, and that gives us the second part, the income effect. All right, so that's how we're going to do this. But the problem is, looking at this, is what is M prime? What is the amount of income you need in order to keep real income constant? And there's no definitive answer to that, what it means by keeping real income constant. Because look at that red budget line. If you look at real income in terms of X and compare it to the original budget line in blue, notice that the hypothetical red budget line there, notice that the horizontal intercept is lower than our original blue budget line. Right? So that says that your real income in terms of X has gone down if you're on the red budget line. But look at the real income in terms of Y. That's the vertical intercept. And notice on the hypothetical red budget line, the vertical intercept is higher than the original blue budget line. So if you had the hypothetical red budget line, you would actually, your real income would actually be higher in terms of good Y. Right? So in some sense, how do we define real income being constant? You're worse off in terms of good X, you're better off in terms of good Y if you're on this hypothetical budget line, right? So we need to, when we say that we want to change income, nominal income, to M prime to make real income constant, there's no way of saying definitively what that number should be. So we actually have two different definitions that are popular in economics on defining what we mean by keeping real income constant. The one definition is going to be used by Sir John Hicks, and the second definition is going to be used by Eugene Slutsky. So we'll look at both of those definitions, and I'm also going to show you a third method, which is a variant on Hicks. It uses pretty much the same definition, but it's a slight change to it, as we'll see. Okay, so just be aware that there's no definitive way of defining what we mean by keeping real income constant. Because in terms of X, your real income went down. In terms of Y, your real income goes up on that red budget line compared to the original budget line. So we need to define what we mean by keeping real income constant. So let's take a look at the first definition by Sir John Hicks. All right, so this is going to be how we're going to decompose the change in quantity demanded from the price change into the substitution and income effect using Hicks's method. Okay, so this comes from Sir John Hicks's book, Value and Capital. If you're interested, this is back in the time when economists could still write, so he was a good writer. It's a very easy to read, and it's basically the material that we've been doing, at least the value part. The capital part is more on the production side. All right. Anyway, so this is the idea that Hicks develops in Value and Capital. He won the Nobel Prize, by the way, one of the greats in economics that perhaps people outside of economics do not know very well. All right, so let's consider the situation here. The example we had in last week is that your original price of X was 9, and the original price of Y is 16, and you had income of $288, and there's your budget line in blue there, your original budget line. And we chose a bundle, we'll call it X naught, Y naught here. Right? That's on your most preferred affordable bundle, given those prices and income. And then we said, well, the price of income goes up to 16. Right? So now your new budget line is the pink budget line there. And we choose, again, the most preferred affordable bundle now, and it's called this X and Y in for the new bundle. Right? Now we know that if it's not a given good, then if the price of X goes up, that the quantity demanded X goes down, which is indeed the case here. So you can see this is not a given good. But we want to break that up into the income substitution effect. How much was that decrease in quantity demanded from the price increase was due to the income effect, and how much was due to the substitution effect? So Hicks says, okay, we're going to define real income as being unchanged if utility is unchanged. So that's his definition. If a utility is still the same as the original bundle, X naught, Y naught, then we say real income is unchanged. That's his definition of keeping real income constant. Okay? So how do we do that operationally? Right? What we're going to say is we want the relative prices to change. We want those, the relative prices. We want prices to change behavior. So we're going to keep the new prices, like we have on the new budget line, but we're going to change the income level to shift up the new budget line parallel, right? So keep the same relative prices, but have more income. And we're going to increase the income such that it's just tangent to the original indifference curve. All right? So that's what we've done here. So you notice the hypothetical red budget line now has the same slope as the new budget line, so that is the same relative prices, but we give them enough income such that when they choose the optimal bundle, the most preferred affordable bundle on that hypothetical budget line, it will give them the same utility as we originally had. That is, it's on the same indifference curve. Right? Okay. So we know that at the tangency, by the way, the slope of the budget line is equal to the slope of the indifference curve. So that will be where the most preferred affordable bundle is at x prime, y prime. All right, so given that Hicks has defined real income being unchanged if utility is unchanged, then we see going from the quantity demanded at x naught to the quantity demanded at x prime, right, going between those two bundles, utility hasn't changed, so the change in x is purely the substitution effect. Right? We've kept real income constant according to the definition of Hicks of keeping utility constant. So any change in x is a substitution effect. So going from x naught to x prime, it's a substitution effect. And then we can see going from x prime to xn, right? That's the income effect because we just have a parallel shift in the budget line. Right? We're keeping the relative prices the same between the red budget line and the pink budget line. So there's no change in the relative price, no substitution effect. This is all just income effect. All right? So that's how Hicks is going to separate out the substitution effect from the income effect. Right? You just take the new prices, give them enough income, nominal income, m prime, such that at the new prices, they can consume a bundle that puts them on the same indifference curve as the original bundle, that is, have the same utility as the original bundle. Okay? All right, so let's put that together. All right, so again, we want to separate the change in quantity demanded due to the change in the relative price from the change in the quantity demanded due to the change in real income. We want the substitution effect separate from the income effect. Right? But of course, as I pointed out, when the price of x goes up, these two things happen simultaneously. Right? So we're going to separate them out by this method of Hicks, is we're going to shift the new budget line such as tangent to the old indifference curve, the original indifference curve. Okay. We call x prime, y prime the bundle at this tangency. So that's your hypothetical demand if you're on that hypothetical budget line. Right? The shift in the budget line kept the relative prices constant, so we know that was the income effect. So going from the new demand for x, quantity demanded of x, to x prime, that would be going from x prime to the xn, that would be the income effect. So take the difference between those two, and that's the income effect, because it's just purely a parallel shift in the budget line, that's an income change. And then going from x naught, the original quantity demanded, to x prime, that's the substitution effect. Right? Because we're changing the relative prices, but we're holding utility constant, so according to Hicks' definition, we're holding real income constant. All right? So that's how it works. And the question, however, of course, is, what is that m prime? What is the income that we need to hypothetically give the nominal income? We need to give what is the nominal income m prime that the consumer has to have, such that at the new prices, they would choose a bundle and make them just as happy as originally. All right, so how do we find m prime? So that's what we want to go through here. Okay, so here's our example again. So on the original budget line, when the price of x was 9, the price of y is 16, you get $288. We found last week that the most preferred affordable bundle was 16 units of x and 9 units of y. And then we increased the price of x to 16, kept the price of y the same as 16, and you still have a nominal income of 288. And we solved the consumer's problem last week, and we found that in that case, they would consume 9 units of each good, 9 units of x, 9 units of y. All right, so we can see, therefore, when the price of x went up from $9 to $16, the quantity demanded of x fell by 7 units, from 16 to 9. All right, so we want to say, okay, the quantity demanded fell by 7. How much of that fall was due to the substitution effect?
Text speakers online and ready.
And how much is due to the income effect? Okay, So according to Hicks, okay, we want to give them enough income such that they choose a bundle at the new prices, they choose the bundle that makes them just as happy as they were originally. Okay. Now, how happy were they originally? Well, originally they faced the old prices. They had the nominal income M, so the old prices, price of X was 9, the price of Y was 16, you had your income of 288, and we found that the quantity demanded of X was 16, the quantity demanded of Y was 9. So your original utility, X times Y, is equal to, oh sorry, back here, before I got it. How did I get 16 and a 9? Again, we did this last week. We could solve the consumer's choice problem all over again each time, but remember, it's easier just to plug in the income and prices into your demand equation, right, which we got from solving the consumer's problem for general values of income and prices. Right, so if you substitute in income of $288 and the price of X is 9, you'll find that X is 16. If you substitute in nominal income of $288, the price of Y is 16, you find Y is equal to 9. So that's where our demand comes, quantity demanded is 16 and 9. And then we calculate the utility. Well, this person's preferences are represented by the utility function xy. So 16 units of X times 9 units of Y. So his original utility is 144 units of the utility. All right, so we want to say, okay, we want X prime, Y prime to be what the quantity demanded would be of X, a bundle of goods X and Y at the new prices, but given the consumer income of M prime, so they're just as happy as at the old bundle. That is, the utility at this hypothetical bundle, X prime, Y prime, is the same as the original utility at the original bundle, X naught, Y naught, that is 16.9. Okay? So we want that hypothetical bundle to have a utility of 144. Okay? So the question is, what income is going to do that? What M prime, such that at the new prices, will have a utility of 144? Now the new prices, remember, the price of X is 16. So if the price of X and price of Y both being 16, what is the income M prime such that when we choose our most preferred affordable bundle, our utility there will be 144, the same as originally. Okay, so how do we find M prime? Well, it's not that difficult, actually. Let's go through the steps. Right, so our utility function is X times Y. Okay, so what we're going to do is we're going to substitute in the demand function for X and the demand function for Y into the utility function. So for X, we'll put in income divided by twice the price of X, and for Y, we'll put in income divided by twice the price of Y. Substitute that into the utility function, and you get utility is equal to the square of income divided by 4 times the product of the prices. So now we have utility instead of in terms of X, the goods X and Y, we have utility in terms of income and prices. But we know what the prices are. Remember, we're evaluating this bundle X prime, Y prime at the new prices. So plug in the new prices, 16 and 16. So we have that the utility of the bundle X prime, Y prime is equal to income squared divided by 1024. Now we have utility purely in terms of income. But we know one other thing. We know that at that bundle, X prime, Y prime, by construction, that utility, we're going to set the income such that utility is equal to the same utility we had in the original bundle, which was 144. All right, so let's set the utility of the bundle X prime, Y prime equal to the utility of the original bundle, and which we know is the utility is 144. And now it's just a matter of solving out for M, and we see that we have to give you a nominal income of $384 in order for you to be just as happy as you were originally at the new prices. Right? So just to sum this up, let me get you a water in case you're copying this down frantically. Of course, you could just realize again, you could just press pause and do that at your own pace. So I guess I can go on. But I still want to get a drink of water, so hold on. Okay, so let me summarize this. Oh yeah, sorry, the last point. What is that hypothetical bundle X prime, Y prime? Well, it's easy to get. Once we have the M prime, we know what the new prices are. So just substitute it into your demand functions for X and Y, and then solve out. So with an income of $384, the new price of Y being 16, we see the demand for X is 12, and likewise the demand for Y is also 12. All right? So at the, here's the summary. So if the consumer is given an income of $384, but must pay the new prices, they will consume at the bundle 1212, and they'll be just as happy as they were at the original bundle when they had the nominal income of $288 and faced the old prices. Right? So that's the idea. So visually, what does it look like? Let you copy this down again. All right. What does it look like? All right, here's the diagram. Right, so here's the idea. The original bundle was at 16.9. That is, given the original price of X was 9, we had our original budget line 9X plus 16Y equals 288. That's the blue budget line. We increased the price of X to 16, so our new budget line is 16X plus 16Y is 288. That's the pink budget line. And now we choose the bundle 9.9. And then we think of our hypothetical budget line is where we give them $96 more such that they have a nominal income of $384, but face the new prices. So that hypothetical budget line, we call it the income compensated budget line, because you can see we've compensated them with enough income to keep their real income the same. Right? So that income compensated budget line, or the hypothetical budget line, is 16X plus 16Y, the new prices, is equal to 384. Right? The income we needed to keep your real income constant. On that income compensated budget line, we saw you're going to choose the bundle 1212. All right, so now we can split up the change in X. We know that X fell by 7 units from 16X to 9X when the price of X went up. And we can see here how much was due to the substitution effect. Right? Going from the blue budget line to the income compensated budget line, notice that we're changing the slope. So we're changing the relative prices, but we're keeping utility constant, and therefore, according to Hicks's definition, we're keeping real income constant. So going from quantity demanded of 16, quantity demanded of X of 16 to a quantity demanded of X of 12, that's purely the substitution effect, because it's just purely a change in the relative price without a change in real income. So we can see the substitution effect is 12 minus 16 is minus 4. So 4 units of that fall on demand of X was due to the substitution effect. And then the remainder is the income effect. We can see that going from 384 hypothetical dollars to our actual 288 nominal income, we see demand falls from 12 to 9. So the income effect, 9 minus 12, is minus 3. Right, so 3 units of the fall was due to the income effect. All right, so that's how we split out the substitution and income effect. Right? So again, in our policy analysis, we may say, well, we don't want this person to be any worse off, so we're going to raise the price of X because we want to change relative prices to influence people's behavior, but we want to compensate them with enough income so they're no worse off than they were originally. So in this example, we would give them an extra $96, so now the nominal income is $384, but they have to pay the new prices, 16 and 16. So we say that they'd be just as well off as before, but we have changed behavior. The demand will go from 16 to 12 if we compensate that income. Right? So we still get a change in behavior due to the substitution effect, even if we don't want the income effect. Right? So that's sort of the intuition behind the policy analysis. Anyway, so there's Hicks's method of separating out the income and substitution effect. Now notice, just to be clear here, so for Hicks's method, going from X naught to X prime, right, that's the substitution effect. Right? So X prime minus X naught is how much the demand for X changed to the substitution effect. In this case, it's negative because the price of one X went up. And then going from X prime to Xn tells us the income effect. All right? Now, because that's a busy diagram, I thought I'd split it into just show you the substitution effect and show you the income effect separately. So here's again the substitution effect. Notice that we're rotating the budget line along the indifference curve. So we're keeping utility constant, and therefore, according to Hicks's definition, we're keeping real income constant. But we're changing the relative prices. So that change is just the substitution effect. Right? The fall in demand from 16 to 12 is the substitution effect, minus 4. And then, likewise, going from the income compensated demand curve to the actual new demand curve, we're shifting down parallel the budget line. So there's no change in relative prices, so there's no substitution effect. This is all income effect. So the fall in demand going from 12 to 9, that's the income effect. Okay. So notice in this example, by the way, that the income effect is when the price of X went up, the demand for X went down from the income effect. So this is a normal good. Right? Remember, for normal goods, if your income goes up, you demand more. If your income goes down, you demand less. So here your real income is going down, right, from the 384 to the 288. Your normal income going down. The demand went down. So this is a normal good. Okay? If it was an inferior good, it would have went up for the income effect. Okay. So the income effect, again, is the difference between the going from X prime to Xn, and that is the hypothetical demand to the new demand, and substitution effect is from going from the original demand to the hypothetical demand. So we see that according to Hicks' method, the fall of 7 units of X, the change in quantity demanded when the price of X went up, of that fall of 7, we're going to attribute 3 to the income effect and 4 to the substitution effect. Right? So you can think, from a policy point of view, we can compensate this person, as I mentioned before, give them an extra $96, such that we can eliminate the income effect, but we'll still have that substitution effect, so we can still change people's behavior, right? So we can still get them to consume less petrol, and therefore pollute less, without making low-income people poorer. Right? So that's sort of the intuition from a policy point of view. Okay. Before I show you the Slutsky method, which is the alternative, I'm going to show you the Calder method, which is just a variant on the Slutsky method. Now, why is it a variant? Because it treats the definition of real income being constant as being utility being constant. So same idea. Right? Real income is constant, utility is constant. But how the Calder decomposes the change in quantity demanded from a price change into the substitution income effect is slightly different. And let me show you how. Right? So remember, so here's the situation. With the original prices, we have a original budget line in blue there, and our original the original bundle X naught, Y naught, so the quantity demanded of X was originally X naught. And then we increase the price of X and we get the new budget line in pink. We get a new optimal bundle XN, YN, so the new quantity demanded of X is XN. And then we're going to decompose that into the income substitution effect. Now we know what Hicks would do is Hicks would say, well, take the old budget line, take the new budget line, shift it up such that it's tangent to the old indifference curve, right? And then we go the income substitution effect from that. Calder does it slightly differently. He says, take the original budget line, shift it down such that it's tangent to the new indifference curve. Show you that on the diagram. There we go. Take the original budget line, shift it down such as tangent to the new indifference curve. Okay. Now, notice from Calder's definition, the substitution effect now is going from Xn to X prime. Why? Because going from the new bundle to the hypothetical bundle, notice that we're rotating the budget line but keeping utility constant at the new utility level. But we're keeping utility constant, so real income is constant. So going from Xn to X prime, that'll be the substitution effect. We're just changing the relative prices. You can see that because the slope has changed at the budget line. But we're keeping utility constant at the new utility level, so there's no income effect. So that's the substitution effect. And then going from X prime to X naught is the income effect, because you can see going from the hypothetical bundle, X prime, Y prime, to the new bundle, the original bundle, X naught, Y naught, was a parallel shift in the budget line. So that's all income effect. Okay? So just to summarize, right? Before I get to that. All right, so we're going to have a shift in the old budget line, such as tangent to the new indifference curve. And again, the hypothetical bundle, X prime, Y prime, will be at the tangent, this tangency. And again, the shift in the budget line is the income effect, but this time it's not xn minus x naught, right? It's x prime minus x, so it's not xn minus x prime, it's x prime minus x naught, so don't get caught up that, look at the diagram. And likewise, the substitution effect here is going to be xn minus x prime, not x prime minus x naught, like in Hicks. Again, look at the diagram. All right, so just to summarize the difference between the Calder method and the Hicks method. So in Hicks says, we're going to give the consumer an income of n prime so that at the new prices, they're just as happy as they were originally. Right? That is, your utility at the hypothetical bundle x prime y prime is the same as your original utility. When you have the income n prime, you're faced with the new prices, you would choose the hypothetical bundle x prime y prime, and you'd just be just as happy as you were originally. Whereas Calder's method says, give the consumer just enough income such that at the old prices, they would choose the bundle x prime y prime such they'd be just as happy as they were at the new bundle. Okay. All right, so let's see how we could do this for the Calder method. It's the same as the Hicks method, the same structure of how to find the answer, how to find n prime. So let's do that. All right. So in our example, remember the new bundle was 9 units of x and 9 units of y. Since the utility function for this individual is x times y, that means the the new utility is 81. Right? So we want to say for this consumer, we're going to give you enough income, just enough income, such that at the old prices, right, you would choose the bundle x prime y prime such that you have a utility of 81. So what income level is that? What's the n prime? Okay? So again, old prices, so we're using the price of x is 9. We're going to give them an income of n prime such that when they do pick the most preferred affordable bundle, x prime, y prime, it will give them the same utility as the new bundle. Okay? So again, as I pointed out, the methodology is exactly the same as Hicks. So we say, virtually the same. So we say utility is x times y, so we substitute in the demand functions for x and y. So therefore we get utility as a function of income and prices, just like before. But now we're going to put in the old prices rather than the new prices. So we put in the prices 916, and we see that we need the utility of that hypothetical bundle x prime y prime to equal the square of income divided by pi 76. We want that utility to be the same as the new utility, so we want that to equal 81. So just solve out for that, and that gives us that n prime. In this case, it's $216. And then once you have that, sorry, go back here in case you're... There you go. Let me take a drink of water and let you fill this in. So this is one of the problems with not having you here. Usually I look up and see what people are writing to give an idea when you're done. Now, of course, the advantage is that even if I do go too fast, you can just press pause. But I don't want to go too fast. Blaze through too much material that you can't handle at once. So I'm trying to slow down here. Okay. So the last part, just to solve out what are those hypothetical demands, x prime, y prime. Right? Well, facing the old prices, 916, if we give you an income of 216, then plug that into your demand functions, and we'll see that the demand for x, the quantity demanded of x is 12, quantity demanded of y is 6.75. Again, I'm going too quick. Okay, so just to recap, if the consumer is given an income of $216, but has to pay the old prices, 916 for X and Y respectively, then the most preferred affordable bundle will be with coin demand of X of 12, coin demand of Y is 6.75, and they'll be just as happy as they were at the new bundle. Okay. So on our diagram, you fill that in. Okay, so on our diagram, this is what it look like. Right? The hypothetical budget line, the income compensated budget line, would have a nominal income of $216, but same slope as the original budget line because you have the old prices. But it'd be just tangent to the new indifference curve. Right? Again, I want to separate out the substitution and income effect to see it more clearly on the graph. I'll let you draw the income compensated budget line for Calder method here, and then I'll do the next slide. Actually, I don't remember whether I've included the Calder budget line there in your lecture notes or not, so maybe you're just waiting for me to go. So I'm going to go. If I'm going too quick, you just hit pause. Okay. So just to separate them out, I'll get back to this in a second. But notice, compared to the, I'll show these numbers in a second. But notice that compared to the Hicks effect, the Hicks method, the substitution and the income effect are reversed. In the Hicks method, the income effect is -3 and the substitution effect is -4. So you get a different answer depending which method you use. Right? Of course, the total change in X is always the same. We observed that the coin demand of X went down by 7. How much you attribute to the, well, that form, the coin demand, and how much you attribute to the substitution effect, and how much you attribute to the income effect is going to depend upon the method you use. The Hicks method says the substitution effect is -4 and the income effect is -3, and here the Calder method's the reverse. Okay, so I want to show you the substitution and income effect separately on the graph because the other one graph is a bit busy, and to show you why it's -3 and -4. Oh, I guess I didn't do that. My apologies. I did for the Slutsky and the Hicks, but I didn't do it for the Calder. So let me go back to the diagram, the busy one then. All right, so I didn't separate this one out, all right, into the income substitution effect diagrams. But we can take a look at it. So what happens here? The original budget line in blue, we have our most preferred affordable bundle 16.9. On the new budget line in pink, we have our new most preferred affordable bundle 9.9. And then we have our hypothetical budget line there in brown, where we would choose the bundle 12, 6.75. So we can see the substitution effect here, right? The income effect is going from the original coin demand 16 to the hypothetical coin demand of 12, because that's just a parallel shift in the budget line, so that's an income effect. Right? So the decrease from 16 to 12 minus 4, that's the income effect. And then going from 12 to 9, that's the substitution effect, because we're changing the relative price. You can tell by changing the slope of the budget lines, but you're still on the same indifference curve, the new indifference curve. So there's no income effect according to the definition that real income is unchanged if utilities are changed. Right? So that's why the substitution effect is -3 and the income effect is -4 in the Calder method. Okay? So don't get caught up in the definition xn minus x prime, because for the Hicks method, xn minus x prime is the income effect. Here, xn minus x prime is the substitution effect. Right? You have to think of it in terms of the diagram to figure out which is the substitution effect and which is the income effect. All right, so the other method is the Slutsky method. So in the Hicks method and the variant, the Calder method, we define real income being constant if utility is constant. The Slutsky method has a different definition of what it means to keep real income constant. Let's see what that is. Okay, so again, this is our original situation. In the original budget line in blue, we have our original most preferred affordable bundle, X naught, Y naught. We raise the price of X. We have our new budget line in pink. We have our new most preferred affordable bundle, XN, YN. You see that this example, it's not a given good, so the price of X went up, the coin demand of X went down. In our example, went down by 7. We want to split that up into income substitution effect. Now, Slutsky method says the following. Real income, we're going to say that real income is unchanged if you can afford the original bundle at the new prices. So we have to give the person enough income such that facing the new prices, they can buy the original bundle that they bought at the old prices. All right? So in other words, facing the new prices of 16 and 16, for price of X and price of Y, how much income do we have to give this individual so they can consume that original bundle X naught, Y naught, which in our example was 16.9. Okay? Now this is actually an easier method to solve, but we don't have to use utility functions or anything like that. Let's see how this works. Okay, so diagrammatically, visually, right, we'll give them enough income such that the new prices, they can consume the original, just enough income, they can consume the original bundle at the new prices. So this hypothetical budget line, it's using the new prices, so it's parallel to the new budget line, right? But it's going through the original bundle, X naught, Y naught, because we're giving them just enough income so they can just afford to buy the original bundle, X naught, Y naught. Okay? So that's Slutsky's definition of keeping real income constant, that you have enough income to afford the original bundle that you bought originally at the old prices. Okay? Now note about this, that even though you can afford to buy your original bundle, X naught, Y naught, on this hypothetical budget line, you would not choose X naught, Y naught, the original bundle, right? You can do better, right? Your most preferred affordable bundles would be something like the bundle X prime, Y prime here. We can see that X prime, Y prime is more preferred because it lies above the original indifference curve. So it's a more preferred bundle, right? So the idea here is, yes, you can afford the original bundle. We're giving you enough income such that at the new prices, you can still buy what you bought originally. However, that's not what you would actually choose. You're going to choose X prime, Y prime, that bundle, because it gives you a higher utility. Right? So now how you can see how, with the Slutsky method, how we can decompose the change in coin demanded into the income substitution effect. Going from X naught to X prime, that's the substitution effect. Right? Both those bundles, X naught, Y naught, and X prime, Y prime, are on the same budget line there, right? So they're both just affordable. So according to the Slutsky definition, it's the same real income, right? On that budget line, you can afford to buy the original bundle, so that's the same real income according to Slutsky. So therefore, the change in coin demand going from X naught to X prime, that's all substitution effect, right? Just from the changing the relative price, as we can see by the change in the slope of the budget line in blue to the budget line in red. So that's the substitution effect going from X naught to X prime, and then of course X prime to Xn, that's going to be the income effect, because it's just a parallel shift of the budget line. So it's just a change in income, no change in relative price. Okay? Now then, in theory, well, theoretically, we actually like the Hicks method better, and the Calder variant on the Hicks method. Why do we like it better? Because in reality, what we're interested in is keeping people's utility constant. That's what we mean by making them just as well off as before. When we're talking about keeping real income constant, right, we want to say they're able to buy, their purchasing power is the same. Well, why are they purchasing goods? Because they get utility from it. So really what we're interested in keeping utility constant. So theoretically, keeping utility constant is what we want to do. Right? That's a nice method of Hicks defining real income constant when utilities constant. That seems theoretically sound. The problem with the Hicks method is that utility is not observable. It's not something we see in the data. I don't know what your utility function looks like. The only thing I get to observe from you are the decisions that you make. I say, well, based on these prices, you chose this bundle, right? You chose to consume this much X and that much Y. And in a different set of prices, you chose a different bundle, that much X and that much Y. Right? I get to observe that in theory in the data. Right? So economists, get data from, say, supermarkets, and they can look at the data and say, well, at these prices, here's how many, here's what the quantity demanded for, say, Sultana brand is, and then we change the price of Sultana brands next week, and we can see what happened to the quantity demanded of Sultana brands. Right? We can get an idea. We get to observe the prices. We observe the quantity demanded at those various prices. So those are the observables. We don't get to observe what the person's utility function looks like. All right. So that the advantage of the Slutsky method is that we only use observables in order to calculate what that M prime is going to be. That is, remember, M prime is, we want to give them just enough income such that at the new prices, they can just afford the original bundle. So we take the original bundle X naught, Y naught, but we use the new prices, right? And then say, okay, how much income do we need to buy those original bundles at the new prices? We give that consumer that much, right? Then see what the hypothetical demand would be. Remember, it's not going to be the original bundle because the relative prices have changed. It's going to be a substitution effect. And then we'll see what the hypothetical demand is. Call that X prime, Y prime, right? So again, the Slutsky method says the hypothetical bundle, X prime, Y prime, is what the demand would be for the goods X and Y at the new prices if you're given just enough income so you can just afford the original bundle at the new prices. Okay? Now, the advantage of this, as I pointed out, is that notice it's easy to calculate that income because that income only depends upon observables. We get to observe X naught, Y naught, what people buy. Right? We see that in the supermarket data, and we know what the prices are. So we can say, let's take this week's prices, the new prices, right? But take last week's demands, the old demands, right? So say, ask yourself, all right, that original demands, quantity demanded, but at the new prices, how much income would the consumer need in order to buy the bundle they bought last week, but at the new prices? Well, we can observe that in the data. We have the prices, we have the quantity demanded in the data, so we can calculate M prime easily. Right? So that's the nice thing about the Slutsky method. The disadvantage, of course, is that the better definition of keeping real income constant is keeping utility constant. That seems like a more pure definition. Because here, yeah, you're keeping the original bundle affordable, but that doesn't really mean much in the real terms. Okay, so let's see the Slutsky method in operation. This is nice and easy. This is the one you like to do because it's much easier than the Hicks method where you have to go through the rigmarole of setting utilities equal to each other. All right, so what is the income do you need to buy the original bundle at the new prices? Remember the original bundle was 16.9. The quantity demanded of X is 16, quantity demanded of Y is 9. But the new price of X is 16, and the price of Y didn't change, it's still 16. So evaluate at the new prices, we see you need $400 in order to buy the original bundle at the new prices, right? Of course, your nominal income is only $288, right? So we'd have to give you $112 to make you just as happy and to allow you to buy your original bundle at the new prices. All right? So that's easier to calculate M prime here compared to the Hicks method. Right? And then, of course, just plug it into the demand equations, and we can get what the hypothetical bundle is. So if we give that consumer $400, that consumer has a nominal income of $400, right? Then at the new prices, they would choose the quantity demanded of X of 12.5. Okay. So the income effect is Xn minus X prime. Let's go back. Well, why it's Xn minus X prime? Oh, because I have it on the next diagram. I'll show you in the next diagram. Okay, so the income effect is xm minus x prime, right? So the original, so the new coin demanded was 9. X prime here is 12.5. So the income effect is minus 3.5. Substitution effect is x prime minus x naught. Again, I'll show you this on the diagram. The hypothetical coin demanded is 12.5. The original coin demanded was 16. So again, the substitution effect is minus 3.5. Again, remember the total change of coin demanded, we already know that from the data, it's minus 7. But you can see the Slutsky method split the change of coin demanded equally into the income substitution factor equal, minus 3.5 each. All right, so notice that all three methods split the change of coin demanded into the income substitution factor slightly differently. So it depends on which method you actually use. The Hicks method is probably the, and the Calder variant are more pure, but this one is better in practice for applied work because it uses observable data. All right, so again, let's take a look at what it looks like graphically. All right, so with the Slutsky method, right, we take the new places, so we're going to have the same slope with the new budget line, that is the pink budget line, but we're going to increase income such that they have enough income to just afford the original bundle, 16.9. So we saw that you have to give them an income of $400. They have to have an income of a nominal income of $400, such that the new prices of 16.16, they can just afford the original bundle 16.9. Right? So the income compensated budget line is 16x plus 16y is equal to 400. But as I pointed out, right, that's not what they're going to choose on that hypothetical budget line. They could do better, and we saw that they will actually choose to, if they had a nominal income of 400 and had to pay the new prices, they would actually choose the bundle 12 and a half. All right, so let's break this into the substitution and income effect. We see that the decrease in demand, we know it goes down by 7 from 16 to 9, but the decrease in demand from 16 to 12.5 right, is the substitution effect, right? Because we're changing the relative prices, but according to the Slutsky method, we can still afford the original bundle on the red budget line, so real income hasn't changed. So that's all substitution effect going from 16 to 12.5, so that's minus 3.5. And then going from 12.5 to 9, that's just a parallel shift in budget line, so that's our income effect again. And that's just a fall of 3.5 as well. All right? So again, I think I separated this out. Right? There's the substitution effect because we're rotating the budget line, so we're changing the relative prices, so that's a substitution effect. But according to the Slutsky method, because we can afford the original bundle on that red budget line, our real income, because we can afford the original bundle on that red budget line, our real income hasn't changed. So real income unchanged, but the relative prices changed, then that change in coin demanded is a substitution effect. And then changing the, shifting the budget line, keeping the relative prices the same. Since the relative prices have not changed, there's no substitution effect, so this is all income effect. Okay. Now, that's the methods we have for separating out the substitution and income effect. And I told you why we want to do that in that policy example, reducing pollution. We want to change people's habits. We want them to pollute less, and the way we're going to do that is to get them to drive less, and the way we're going to do that is to raise the price of petrol. But we don't want to make these people worse off because it primarily affects the low-income people. So we're going to compensate that to eliminate the income effect. So you can see why it's important now. What I want to point out here is something, an interesting issue that happened in price indices. This is something an area that I worked in, but it became a big issue in the 1990s. Let me give you an idea what happens here. You're probably familiar with the Consumer Price Index, right? It's a measure of inflation. What it does is it takes what it calls a typical bundle for consumers. So, a typical household, how much they would spend on housing. If you own a house, it's a rental equivalent. So how much you would rent that house for. So a typical price for an average house, that's the rental price of the house. How much they spend on food, how much they spend on entertainment, so on. And break it down into various categories. And they say, okay, that particular bundle that you typical household will buy at a particular point in time. We take the prices at that point in time, and then over time, we keep that same bundle, but we evaluate it at the newer prices and see how much that costs. And then that's our measure of inflation. To say, well, you know, that bundle, you would need an income of, say, $288 to consume that original bundle, but now at these new prices, to consume that same bundle, you would need $400, right? And that gives you a measure of inflation, right? 400 minus 288 is 112 over 288. I don't have my calculator on me, but that will give you a measure of how much inflation you've had between those two time periods. Right? That's exactly what the Slutsky method is, right? So with the CPI, what it does is it takes that original bundle, the one we had at 16.9, I don't know why 16.9 is not on here, I should have put it back in there. So take that original bundle at 16.9, right? That's what the CPI would take. As you say, that's your typical bundle, that's what we're starting with. Right? How much does it cost to buy that original bundle? What the original price is, you need an income $288 to buy the original bundle. But then the prices change. In this example, the price of X went up to 16. And then we say, well, how much does it cost to consume that original bundle? And we know, we just saw, it costs $400 at the new prices to consume the original bundle. All right, so CPI says inflation has gone up. All right, you need $400 instead of $288 to consume the original bundle. And that's how we determine inflation. But look what happened here. Right? Suppose we, as a government, we say, okay, we have this inflation. We don't want pensioners to be worse off because of inflation. So we say, okay, well, initially, you know, we used to send them a check for $288 so they could buy this typical bundle, $16.9. But now prices have gone up, and now we see that to buy that bundle $16.9, we have to send them a check of $400. So suppose they do that. They send a check to $400 to pensioners to make them just as well off as they were before. They can buy the original bundle. However, that's not what happens here. As you can see, there's a substitution effect that goes on here. Even though you send them enough money to buy the original bundle, the relative price of X has gone up, so they still want to consume less X and consume more Y. And we saw that the optimal bundle here now, instead of 16.9, right, with their $400, they're going to not buy 16 units of X and 9 units of Y. They're going to buy 12.5 units of X and 12.5 units of Y. That gives them more utility. So notice that if we increase pensioners' checks in line with the increase in inflation as measured by CPI, we're actually making pensioners better off. Now, it's only slightly here, but over time, that adds up. Right? Year by year, increasing percentages, eventually that adds up to a significant amount. And this is what the economists came around to realizing, is that these measures, using CPI as a measure of inflation, overestimates the true cost of living to people. So if we're increasing people's pension checks or unemployment benefit checks or welfare checks or so on and so forth in line with inflation, or, for example, unions would often bargain for, say, a 3% real wage increase plus whatever the CPI inflation is. Again, that's going to give you more than a 3% real wage increase because the CPI is overestimating the true cost of living. So over time, what happens here, therefore, is that you're actually making these people better off rather than just as well off. Right? The better method would be the theoretical one from Hicks, and that is just to give them enough income such that they have the same utility as originally. That is, we should give them the utility, increase their income to $384. $384, not to $400. If we increase the income to $384, we saw they would choose the bundle 1212, which makes them just as happy as the original bundle at 16.9. Right? Both of those utilities under 44. Right? So that's turned out this theoretical issue of using Slutsky method instead of the Hicks method leads to overestimating the cost of living, and therefore all these contracts where your wages are going up in line with inflation, or pension checks are going up in line with inflation, and so on and so forth, are actually making recipients better off over time, increasing the purchasing power of these individuals. So economists have realized that CPI as a measure of inflation is actually overestimating the true cost of living, and they're trying to make these adjustments for that. So I just want to show you again something that was fairly theoretical turns out to have enormous practical implications for people. Okay, that's the income substitution effect lecture. Because I have 37 minutes left, I'm going to go over the elasticity lecture notes, and all the elasticity ones are actually fairly straightforward. Oh, get rid of that for you. There we go. Okay, so unlike the income and substitution effect lecture notes, which were fairly conceptual, elasticities are straightforward. Nothing difficult about them. So we should be able to go through this relatively quickly. If I don't finish it today, I'll do it on Wednesday. Finish it up on Wednesday. I also uploaded lecture notes on consumer surplus, so we'll probably get to that on Wednesday as well. All right, so let's go over the demand elasticities. Go back here. Okay, so demand elasticity, the idea is we're going to have these measures of how responsive demand is, quantity demanded is, to changes in other variables like prices or income, or prices of other, like the price of the good or income or prices of other goods. Those are the three main ones. All right, so how responsive is demand, quantity demanded to changes in other variables? We're going to use this elasticity measure. Now, just to give you an idea why we use elasticity, the obvious thing to use initially when you want to say, well, how does quantity demanded change when the variable change, is to use a slope. All right? So, for example, if we want to say quantity demanded change when the price change, why not just take the change in quantity demanded from a change in price? Right? That is the slope of the demand function. The inverse of the inverse of the slope of the inverse demand function. Now, from the slope, we can tell the direction of the change. So, if we remember, for anything but a Giffen good, and remember, Giffen goods are extremely rare if they exist at all. But other than the Giffen good, we know that demand curves slope down. So, when the price of X goes up, the quantity demanded goes down. So we know the sign of the change, the direction is going to be negative, but we're interested in the how much they will change, right? How much will quantity demanded of X change when the price of X goes, when the price of X changes? So in the previous example, we saw when the price of X went up from 9 to 16, the quantity demanded of X fell from 16 to 9, fell by 7 units. So we want to say we know demand curve slope down, so the price goes up, quantity demand goes down, but by how much? Right? Well, the natural thing is to use the slope estimate to see how much it changes, right? So take the change in X or the change in the price of X. Now, if the demand curve is differentiable, we can just take the derivative, right? The derivative of X with respect to the change in price of X. Right? The problem with using the slope is that the value you get out for the slope depends upon the units of measurements. Right, so I made an example here. Right, so suppose that the price of platinum goes up by $200 Australian, right, and that caused the demand for platinum to fall by 40 kilograms. Right. Now notice if you're calculating the slope, delta x over delta px, right, that is the slope of the demand function, then you'll get a different answer depending on the units you use. So in this example, I changed the units of the quantity demanded, the units of X, using either kilograms or troy ounces, and likewise I changed the prices using either Australian dollars or US dollars, with the Australian dollars with 71 cents US, if only. This is last year's data. And notice in all four cases, we'll give all four combinations of units of measurements. We get four different measures of the change in slope, anything from minus 0.2 all the way up to minus 9.06. Right? So that's unfortunate. We don't want to. We want to say how much did the quantity demanded change when the price changes, but we don't want it to depend upon the units of measurement. Right? So to get around that, we use percentage changes, because percentage changes are independent of the units of measurement. Right? So to give you an example, right? If the price of platinum increased from 1,000 to 1,200, that $200 increase Australian, that's a 20% increase. But if we used U.S. dollars, then 1,000 Australian is $710. If we use the exchange rate I have there of 1 Australian dollar is 71 cents U.S., then that's an increase in price from U.S. 710 to U.S. 852. That's still a 20% increase in the price. So whether we use Australian dollars or U.S. dollars is still a 20% increase. Likewise, whether we use kilograms or troy ounces, we'll get the same percentage change in the quantity demanded. All right, so that's the nice thing about percentage changes, is they're independent of units. Okay, so we want to talk about how does the quantity demanded change when we change another variable. We're going to use percentage changes rather than actual unit changes, so we can eliminate this problem of units of measurement. All right, so that's why we're going to use what we call the elasticity measurement rather than actual units. So we define the elasticity of x with respect to y is simply the ratio of the two percentage changes. Percentage change in x divided by percentage change in y. So you can create an elasticity for any two variables as long as you can calculate the percentage changes in those variables. All right? So what we're interested in today's lecture are elasticities to do with the demand function, quantity demanded. So we're going to have the numerator is going to be the percentage change in the quantity demanded of x, right, or quantity demanded of y if we're using y. But the numerator is going to be the percentage change in quantity demanded. And then the denominator can depend upon the variable we're interested in, whether it's the price of good x, the price of other goods, or income is the ones we'll look at today. Okay? And then later on, for example, we could also do other elasticities. So if we look at the supply side, we might want to look at the percentage change in quantity supplied due to the percentage change of some other variable. Right? That'd be a supply side elasticity, and we'll get to that one later on. And there's other elasticities you can do as well. Right? Just the ratio of two percentage changes. Right? So in this lecture note, the numerator is always going to be the percentage change in the quantity demanded of the good. Okay. And remember, there's no elasticity has no units. Right? All the units cancel out when you do percentage change. Right? The change in x is in one unit, but you're dividing it by x, so the units cancel out. So elasticity is simply a number. There's no units attached to it. Right? So it's just 5 or minus 6 or whatever. It's just a number. Okay. All right, so let's do the first elasticity, the elasticity of x with respect to y. Right? So the elasticity of x with respect to y, as I said, is just percentage change in x divided by the percentage change in y. Now remember, for percentage change, you just take the change in x divided by x multiplied by 100. Percentage change in y, you take the change in y divided by y multiplied by 100. So notice that the 100 in the numerator and denominator cancel. So it's just a change in x divided by x all over the change in y divided by y. Now we can just rearrange those terms by multiplying numerator and denominator by xy, and we get that the elasticity of x with respect to y is a change in x divided by change in y times y over x. Right? So in other words, it's the slope, delta x over delta y, right, times the quantities y over x. Now, we actually have two variants of how we calculate elasticities. You may want to calculate elasticity between 2 points on a curve. Right? We call this the arc elasticity. So we want to calculate the elasticity between 2 points x1, y1, x2, y2. What we do, using our definition, we want the change in x divided by change in y times y over x. Now, the change in x divided by change in y is trivial. Right? Just take a look at how much x changed from x1 to x2, how much y changed from y1 to y2, and we can get the change in x divided by change in y. That's not a problem. The problem is the y and the x. What are you going to use for the quantity y, and what are you going to use for the quantity x? Because we have two x's and we have two y's. Well, it's conventional just to take the average of the two. All right? So for x, we'll take the average value of x, and for y, we'll take the average value of y, and we use that for the y and the x respectively, x and y respectively. Okay? So that's the arc elasticity demand. Typically, what we're going to use in this course is what we call the point elasticity demand, and that is, instead of calculating the elasticity between 2 points, we're going to calculate the elasticity at a point, and we call this the point elasticity of x with respect to y. All right. Now, how do we calculate that? Well, instead of taking the slope between 2 points, we're taking the slope at a point. So in other words, we're taking the slope of the tangent line. Remember, the slope of the tangent line, however, that's the definition of the derivative. So the definition of point elasticity is the slope times y over x, but the slope is the derivative, so it's just the derivative of x with respect to y times y over x. Okay? So this one's much more convenient to work with if you have differentiable functions, but of course it does require differentiability, which generally we'll assume, although not always. Okay. All right, so let's see how this works. So again, in this lecture, it's all to do with the demand side. So we're going to do all elasticities that involve the percentage change in the quantity demanded. The first one is going to say, well, what's the percentage change in the quantity demanded if we change prices by a certain percent? All right, this is what we call the price elasticity demand, or if you want to be more fussy, the own price elasticity demand, because you're changing the price of the good, its own price. All right, we use the Greek letter epsilon to represent the price elasticity demand, because this is the most popular elasticity that we use on the demand side, and perhaps probably the most popular one of all economics. So it gets the letter E for elasticity. Right? So this is going to be a measure of how responsive demand is to a change in its own price. Right? If price goes up by 10%, what's the percentage change in quantity demanded? Right? That's what the elasticity demand is going to tell us. All right, so let's see how this works. Now, a little note about this for notation. Now, except for given goods, we know demand curves slope down. All right, so the change in quantity from the change in price is going to be negative. If the price goes up, the quantity demand goes down. All right, so since it's always going to be negative, that means the percentage change in quantity demand from percentage change in price would always give us a negative number. All right? Now, we don't, because we're always going to get a negative number, sometimes it's just convenient to say, all right, we already know that the price elasticity demand is going to be negative, so we're just going to drop the negative sign. All right? That is, we're going to define the price elasticity demand to be the negative of the percentage change in quantity demand or the percentage change in price. Now, we're going to turn the negative into a positive number. Right? So we understand that when the price goes up, the quantity demand goes down. That's always going to be the case. So let's just drop the negative numbers so it's easier to work with just with positive numbers. Okay? That's just a convention that a lot of economists use. All right? A couple of notes about that. As I pointed out, this is the most popular elasticity that we use in economics. So when we say elasticity demand, we mean this own price elasticity demand. That's the one we refer to when we say elasticity demand. It's the one we use the most. And secondly, I dropped the minus sign here. That's a popular way to do it, but not every economist does this. So some books may say, or studies may leave the negative sign in. But that's not difficult to pick up on this, right? If you leave the negative sign in, then it's always going to be negative for all the elasticities, right? Because it's always negative. If you drop the negative sign, then it's always going to be a positive number for elasticity, because they're always the same sign. So it's clear one way or the other. Doesn't matter whether you drop it or not. You should be able to pick up on it right away. Okay. So what does it mean, the elasticity demand? What's it telling us? So as I pointed out, the larger the elasticity of demand, it's going to tell us that demand is more responsive to a price change. So you can think of that. For example, if the elasticity demand is 2, right, then that says if you percentage change in prices, say, goes up by 10%, right, prices go up by 10%, then that says that the quantity demanded is going to fall by 20%, right? 20 over 10 is 2. So the elasticity is 2. Now, if the elasticity of demand is 3, a higher number, that says when the prices go up by 10%, the quantity demanded falls by 30%, right? It falls more, right? So that's a more responsive change in demand to the same change in price. So the higher the elasticity, the more sensitive demand is to a change in the price, okay? We say that in that case, it's more elastic. That's the way we respond for elasticity. Right? So the higher the elasticity demand, the more sensitive demand is to a change in the price. We say that demand is more elastic. So a few definitions you can just see here, reasonable definitions for elasticity. If the elasticity is 0, right, then we're saying when the price of X goes up by 10%, quantity demanded doesn't change at all, right, then we say that demand is perfectly inelastic, absolutely no change in demand. Right? If elasticity is less than 1, we say demand is inelastic. So here the price of X goes up by 10% and say that the quantity demanded falls by, say, 8% or 5% or something like that, falls by less than 10%. All right, so the elasticity would be less than 1. In that case, we say that demand is inelastic. If elasticity is 1, demand is said to be unit elastic. So that says if prices go up by 10%, quantity demand falls by 10%, so on and so forth. And then if elasticity is greater than 1, demand is said to be elastic. I already did an example. And if elasticity is infinite, the demand is said to be perfectly elastic. Right? You change the price even the slightest little bit, and then demand changes by an infinite amount, theoretically or hypothetically. Okay? Let's see what that looks like on our demand curves. Okay. All right. Suppose demand is completely unresponsive to its price. Right? So the price goes up by 10%, but the quantity demand doesn't change at all. Right? So the elasticity is 0. What does our demand curve look like? Right, when the elasticity is 0? Well, we saw it. Right? The price goes up by 10%. Since the elasticity is 0, that means the numerator has to be 0. Right? The quantity demand doesn't change at all. Right? So our demand curve must be vertical. Right? As the price increases or decreases, demand doesn't change at all. We stay at the same quantity. Okay? So an elasticity of 0 gives us a vertical demand curve. Now, it's hard to come up with examples of perfectly inelastic demand, but you can think of an approximation, maybe a heroin addict. And if the price of heroin goes up by 20%, they still need their heroin, I guess, so they'll pay the extra 20% and still consume as much heroin as before. Having said that, by the way, I think there's some economists that do studies and find that even heroin addicts will respond to price changes. But something like that. There'll be very inelastic demand for heroin addicts. Right? So very, very unresponsive to changes in the price. So think about goods that you buy that you're not very particularly responsive to the change in price. Right? If for example, your data plan goes up by a little bit, by 10% or 20% on your mobile phone, would you still use as much as before? You may not change your behavior very much at all. If you don't change your behavior at all, then in that case, the elasticity demand for your mobile data usage is 0. You completely inelastic demand, perfectly inelastic demand for mobile data usage. Right? So it depends on you. So think of an example for yourself where if the price went up by 10, 20% or something, you say, it wouldn't affect me, I still buy it. I wouldn't change the amount that I buy of that good. Okay? All right, to get a feel for the relationship between demand curves and elasticity, what we're going to do is the following thought experiment. Okay? We're going to use the point elasticity demands. And what we're going to do is we're going to rotate the demand curve about a point. So let's pick a point, P star, Q star, that's on some demand curve. And then we're going to rotate the demand curve around that point. Okay? Now, since we're keeping the same point, we're going to evaluate the elasticity at that point, PQ. Since we're keeping P and Q the same, then notice in the definition of elasticity demand, P divided by Q hasn't changed. That's just the constant. So So the only way the elasticity is changing is when the slope term changes, right? dq dp. Right? So we're going to change the slope, but not change p over q. We're just going to rotate along that point, changing the slope, and ask how the elasticity changes. Now, one problem, however, we can blame Alfred Marshall again. Remember, Marshall does not put the demand curve, when he draws demand curve, does not use the demand function. He uses the inverse demand. Remember, we use P on the vertical axis and Q on the horizontal. So we're getting P as a function of Q. That's the inverse demand, rather than Q as a function of P, which is the demand function. All right, so the problem here is, in the elasticity demand, right, the derivative dq dp, that's the slope of the demand function, right? But when we draw the demand curve, we're getting the slope of the inverse demand function. So just be careful. We're getting dp dq when we draw the demand curve, thanks to Alfred Marshall. So when you think about that, the flatter the demand curve, right, that is dp dq is lower, that means dq dp is higher, right? So that means that the flatter the demand curve, dq dp is higher, and therefore the elasticity demanded will be higher. Right? So the more elastic, the flatter demand curve, the more elastic demand will be. That is, the more sensitive the consumer is to changes. The more sensitive the consumer is to changes in the price. Right? Same price change will lead to a larger change in quantity demanded for a flatter demand curve than for a steeper demand curve. Okay. All right, so this is what it looks like visually. Right, so again, the vertical demand curve is perfectly inelastic. Elasticity demand is 0. And now we're going to rotate around the point PQ. So holding P and Q constant, that means the elasticity is only going to change with the slope. And we say if the slope gets flatter here, dp dq is smaller, which means dq dp is larger, which means the elasticity is larger. All right, so as we're making the slope of the demand curve flatter, we're making the elasticity higher, more elastic. And then you can think, in the thought experiment, making the elasticity perfectly, making the demand curve perfectly horizontal, that drives up the elasticity to infinity. All right? So when demand is infinitely responsive to the price, we know elasticity is infinite, and that looks like a horizontal demand curve. Right? So on the horizontal part of this demand curve, demand is infinitely elastic. Right? So you can sort of think of this as, right, if you're on the horizontal part of the demand curve, right, if you raise your price even the slightest little bit, demand falls exactly to 0. Right? Suppose that P upper bar, P bar there is $10, and you try to charge $10.01. As soon as you try to charge a penny more, all of a sudden demand falls to 0. Right? If you charge a penny less, to $9.99, demand goes off to infinity. Right? So that's the idea as an extreme case. Right? So for horizontal demand curve, elasticity is infinite. For vertical demand curve, elasticity is 0, and then in between, elasticity is finite, between 0 and infinity. Okay. All right, so you get a feel for that now on the relationship between elasticity and demand curves. Now we use linear demand curves a lot, just because they're easy to work with. Not that necessarily people have linear demands. But let's show the relationship between elasticity of demand and the linear demand curve. Okay, so with the linear demand curve, we can write that as the quantity demanded is equal to A minus BP, where A is the vertical intercept constant, as the vertical intercept, and minus B is the slope. Right, so B is positive, so minus B is negative, downward sloping demand curve. All right, so there's our demand function if it's linear. Now, since the slope is constant by definition for a linear demand curve, as you can see here that the slope here is minus b, is constant. So minus the dq dp, if you differentiate the quantity with respect to price, you get minus b. So the minus of it is plus b. So we plug that into our elasticity of demand formula and place of minus dq dp, we can just put b, all right, the constant. So that means the elasticity of demand only changes as p over q changes, right, since the slope is constant. All right, so let's do that. Let's change p over q. As we move up the linear demand curve, the price is going higher and the quantity is going down, right? Because remember, demand curve slope down. So if you go up the demand curve, price is higher, quantity is lower, and therefore as you go up the demand curve, P over Q is increasing, and therefore the elasticity is increasing. All right? So as you move up the demand curve, demand becomes more elastic, right? Points higher in the demand curve are more elastic. Now at the horizontal intercept, right, the price is 0, right? So P over Q is just 0, that means the elasticity is 0, right? So completely inelastic at the horizontal intercept, and then as we move up, the demand curve becomes more elastic until we get to the vertical intercept, where it goes off to infinity. Now of course we can't divide out by Q equals 0, so that's why I say Q approaches 0, P over Q approaches infinity. So you can't take this to a math person and get them to complain about that. Right? By the way, the general formula for a linear demand curve in terms of prices, right? As I pointed out, the negative of the slope is just B, and quantity is equal to A minus BP. So in terms of the price, we can write the elasticity of a linear demand curve as B times P over A minus B times B. So you can plug in a price and calculate the elasticity demand from that formula if you like. That's not a big issue, but I thought I'd show you too. All right, so here's what it looks like for a linear demand curve. At the horizontal axis, here is quantity of 14. The elasticity demand is 0. As we go up the linear demand curve, the elasticity increases. So initially, it goes from 0 to a positive number, but less than 1. So that's inelastic demand. And then it hits 1, that's uninelastic, and then becomes greater than 1, that's elastic, and then as we go off to the vertical intercept, it goes off to infinity. Right? So that's the idea for a linear demand curve. The elasticity changes as you move along the demand curve. Okay. You can do a few examples if you like for a linear demand curve. All right, I want to show you an important relationship between the elasticity demand and total revenue or total expenditure. Now I say total revenue or total expenditure because remember, price times quantity, right? That's how much a consumer spends on that good. That's the expenditure by the consumer. But from a firm's point of view, the price times the quantity is how much revenues they're getting. All right, so what do I call expenditure or revenue? Just two sides of the same coin. Now we'll come to the firm later on, but either we call it revenues or expenditure, doesn't really matter. It's just P times Q. Now notice that for revenue expenditure, P times Q, notice that the quantity, remember the quantity, downward sloping demand curve, so quantity depends upon the price in general. All right, so P times Q, both of those terms depend upon the price. So if we want to differentiate revenue or expenditure with respect to the price, right, we're going to have to use the product rule because both of those terms, P and Q, right, are functions of the price. Right, so the product of two terms that are a function of the price. So we need to use the product rule to differentiate. So let's do that. If we differentiate expenditure or revenues with respect to the price, what do we get? We get this expression, right? Product rule, we differentiate the first term, price, with respect to the price, right? It's just 1, multiplied by the second term, which is Q. So 1 times Q, which is Q. And then we differentiate the second term with respect to the price. So that's dQ dP. Multiplied by the first term, which is P. So that gives us our expression that the derivative of expenditures or revenues with respect to the price is equal to the quantity plus the price times the derivative of the quantity with respect to the price. Okay. So we ask the following question. When will an increase in the price increase revenues or expenditures if we're looking at expenditures? Well, we already see now that revenues will go up when the price goes up, or expenditures will go up when the price goes up, if this expression is positive, right? If Q plus P times dQ dP is greater than 0. Now, take this expression and divide both sides of the inequality by Q. Right? Remember, 0 divided by Q is just 0, so the right-hand side is still going to be 0. But dividing the left-hand side by Q, we get 1 plus P divided by Q times dQ dP. Now, can you recognize what's on that second term? That's just a negative of our elasticity demand. Right? So this is 1 minus the elasticity demand on the left-hand side. So we have, therefore, that the revenues will go up when the price goes up as long as the elasticity demand is less than 1. In other words, inelastic. Right? So to summarize, an increase in the price will increase revenues if demand is inelastic. Right? You raise your price, your revenues will go up. Well, if the price goes up and you're the consumer, your expenditures will go up. Conversely, if the price goes down, right, then your revenues will increase if demand is elastic. Right? You lower the price. Right? If demand is elastic, the increase in the quantity demanded will be so big that your revenues will go up. Right? And likewise, if your expenditures are elastic, when the price goes down, your expenditures will go down. So that's a nice relationship to know, the relationship between elasticity and revenues. For inelastic demand, raising the price, if you had a point on the demand curve that's inelastic, then you know if you raise your price, your revenues will go up. If you had a point on demand that's elastic, then if you decrease your price, your revenues will go up. Right? So it's important to know where you're on the demand curve at an inelastic part or an elastic part of the demand curve. Right? So I knew somebody in graduate school who worked at part-time at a department store. I can't remember if it was Myers or David Jones or whatever. And part of his job was to look at data where they would change the prices of goods, every weekend or whatever, that have sales on. Sometimes it'd be 40% off, sometimes 30% off, sometimes 20% off. So they're changing the prices, and then they will see what the change in demand would be, and that'll give them an idea on the demand curve, and they can calculate the elasticities. And so if it was an inelastic demand, that says that they can still raise the prices and increase revenues. Right? If it's elastic demand, it tells them that if they raise the price, that would decrease revenues. And maybe they want to actually lower the price if they want to increase revenues. Now, we're going to see later on, firms are not actually increasing and maximizing revenues. They're interested in maximizing profits. So we're going to have to adjust that a little bit later on. But we'll see how that comes into play. Okay. But you can see that's a very important relationship between those two. All right, the last point I want to make here is the determinants of the elasticity of demand. Now, what determines how elastic demand is? Right? Well, one of the most important determinants is the number of close substitutes. Right? So you think if there's lots of close substitutes, remember, if your perfect substitutes, the goods are identical. If they're close substitutes, they're not identical, but they're very similar. Right? So you have lots of close substitutes, and there's lots of other goods that are similar to the one that you're already purchasing. So think of what happens. If your firm tries to raise the price of the good, and there's lots of close substitutes, then the consumers are going to say, you know what, the price of that good has gone up, but I like these other goods pretty much just as much as this good. So when the price of X goes up, I'll just buy the other close substitute to Y. So that limits the ability of the firm to raise its prices. It tries to raise its price a little bit, but when the price goes up, everyone needs to decide to buy the substitutes, the close substitutes. Right? So demand falls a lot. Right? So now you have very responsive demand. Right? A small increase in the price leads to a large decrease in the price. Right? So we have, therefore, that the more close substitutes we have, the more elastic demand will be. Right? So it's hard for firms with lots of close substitutes to raise the price. So if you look at, for example, Android phones, lots of brands of Android phones, the low-budget ones, right, they're all pretty much fairly similar. So people tend to shop on price or something for low-budget Android phones. So if one company decides to raise their price, right? They may lose a lot of the market share because people just say, well, that low-budget Android phone is just the same as the other low-budget Android phones. So if you raise the price, I'll just buy the other ones, right? So on and so forth. So you can think of lots of examples like that, where if you think Coke and Pepsi are very similar to each other, then if Coke tries to raise the price in the supermarket for Coca-Cola, you just switch to Pepsi. And if lots of people do that, then demand's very elastic. Coke will find it hard to raise the prices, right? That's why, by the way, why firms spend so much time trying to brand their products, right? They want to say our product is different from the competitors, right? There are no close substitutes for us. The more they can convince you there's no close substitutes, right? That you have to have this product because there's nothing close to it, then the less elastic demand is, that it increases their ability to raise prices without losing demand, okay? And therefore revenues go up. Okay? So, for example, I'll give you what are substitutes for a meal at a Vietnamese restaurant. So I want to point out that you can go to lots of Vietnamese restaurants in Melbourne, right? So there's lots of close competitors for a Vietnamese restaurant. You can go to any Vietnamese restaurant. And not only that, if you think that other Asian foods are close substitutes, if you think, well, let's go out for, I don't feel like going out for Asian, and you say, rather than you saying, I want to go out for Vietnamese, you might want to go for a Vietnamese meal, or you're just as happy to go out for a Thai meal, or Chinese, or Indonesian, or whatever, right, Malaysian. Okay, if that's the case, if one's just as good as the other, in the sense of, close substitutes to each other, then it's going to be difficult for Vietnamese restaurants to raise their prices. They try to raise the prices, customers just go and leave and go to other Vietnamese restaurants or other Asian restaurants. Right? So that would be an example where it would be hard. You'd have very elastic demand. Right? What's the other things that matter? Well, I see I'm out of time, so what I'm going to do is finish this up on Wednesday. Again, what I'm going to do is I'm going to try to record the lecture on Wednesday from home on Zoom, upload it to the media gallery in Canvas. If it works, I will send you an announcement. That's where you're going to get the lectures from now on. If it doesn't, I'll be back here in this lecture hall on Wednesday. All right, best of luck. Cheers.